Welcome to another video on our channel, and in this video we're going to go over something that is very integral to higher level programming, that is data structures. You might have heard about data structures from different sources, from different areas, but we need to understand data structures are the concept that are going to take you to a higher or more lucrative programming jobs. All of those jobs, all of the coding interviews that you see, all of these hacker rank, lead code problems, blind 75 problems that we're doing on our channel are going back to the foundations of data structures. Because in most of these coding interview problems for these jobs and other coding placements, getting a good understanding of what data structures inherently are is an essential component. We also need to understand that data structures outside of the coding frame, data structures are also an essential tool that allow developers to efficiently store, organize, and manipulate data. They allow us different ways through which we can manage, optimize performance, and solve specific problems. So, data structures is a combined term that's used to talk about different sort of ways data can be stored. That's the central thing that you need to understand at this particular moment. Data structures is a collective term used to express talk about a group of different structures or ways in which you can collect, store, and um, manipulate data. Basically, that's what you need to understand, right? So based on that understanding, in this particular video, we're going to go over different data structures and what they are, how they're used, and how you can understand more fully. So the first data structure that you need to look into is basically called arrays. So let me use my pen over here, and let's start the writing about that, right? So let's use dark green here for first heading. So first thing we need to talk about is arrays. So what are arrays? Arrays, if you are a Python, if you work on Python, they're also known as lists. So they are an essential data structure for you to understand. Why? Because they are a collection of elements stored at contiguous memory locations. What do you mean by that? So imagine, let's see how data structures generally look first. So generally, in any programming language, you'll have a data structure. Maybe there's a slight difference in some, but in any programming language, you'll usually have a data structure, something like this, surrounded in square brackets. This is what we call an array, right? It could be numbers, or it could be letters like A, B, or C. So it could be anything here itself, right? So this is how arrays look like. So now that you understand exactly what arrays are, the next thing we need to focus on is basically how do you understand arrays themselves. So they're mentioned that they're located in contiguous memory spaces next to each other. What do you mean by contiguous memory spaces, right? So imagine your RAM or your memory is this square box, right? So the memory in your computer is this red square box that we just created, right? Within this square box, there's subdivisions within that space. Let me use another color to refer to the subdivisions. So within this box, these blue lines are the subdivisions of that particular space. So every memory has different memory slots, right? And each of this memory slot is what basically is a memory location where 4 bytes of data can be stored, right? So when we talk about an array, it means letter 1 would be stored here, value 1 would be stored here. Let me use a different color here. So let's say value 1 would be stored here, from here, and 2 here, and 3 here, right? Generally speaking, this is what we mean. So when we have an array, the memory spaces are located right next to each other, right? But you might be thinking, isn't that common sense? No. Because generally speaking, memory usually, when you store something, is stored something like this. This one item is here, one item is here, one item might be here, right? And the only way we can know what is where is basically because every item is, within the variable knows where the second part of that item's memory address is. And each of these blocks usually have a memory address, something like 0, E, F, F, something like that, right? So that is how memory addresses are stored. So these memory addresses, usually data is stored in multiple spaces in based on where memory is available. But with arrays, you need to find contiguous memory spaces because array data must be stored in contiguous memory spaces. So that is the focus for arrays, right? So what are the use case of arrays? That's the third thing we need to focus on in this particular, right? Where are arrays used? So uh, if you look here, right on top of this case here, right? You notice that with both of these lists, we've just used one sort of data type. Either it's numbers or strings or some other data type, right? Because that is a restriction of arrays, right? Wherever you need to store data type of the same type which are related in some manner, to use arrays to store them, basically. So that's why that is one of the use cases of arrays to store multiple items of the same type, such as a list of numbers or names, basically. Now that we understand arrays, we all need to look at the second structure that we need to go over, which is linked lists. So what are linked lists, right? So when we talk about linked lists, they're a sequence of nodes, each node containing data referenced or linked to the next node. Now, I think if we look at how this is saved in the memory, you'll understand exactly what I meant by earlier when I mentioned that arrays must have contiguous spaces, because linked lists do not have contiguous spaces. What they have is a direction to the next item in that list. So a linked list usually is represented by nodes. So let's use the red color to show nodes. We have 3 nodes, right? Nodes basically are spaces where memories are saved, right? And let's say the value stored here would be, let's use a color that's a little more legible, 1, 2, 3. So each node is a memory space that we talked about, right, with a specific address to that memory. Why do we refer to them as linked lists? Because they're single directional linked lists. What do you mean by single directional? So every linked list connects to the next item on the linked list by knowing its address. And the thing is, only the item here knows the address of the item next in the list, right? The item next in the list, which is 2 here, cannot know the direct address of memory number 1. So that is why linked lists are as known as such. So this is what a linked list is. We have nodes, and then we have every node telling what the next item would be. In this case, on the last item on the node, it would be linked out basically to the null value, letting us know that the linked list is done basically. So this is why how simple linked lists this is where linked lists are as a data structure in Python. And learning to manipulate is a major challenge because this is one of the most common asked problems within programming interviews. So what is the use case of linked lists? Basically, you need to understand linked lists are extremely useful for dynamic memory allocation, where basically when we need to frequently insert or delete elements, where we can go to a specific node, delete that element and replace it with something else, or insert some element at a certain space. So that's why linked lists are important in that particular use case. I'm not going to go to specific use cases here because we're just going over the different sort of data structures, what they are, and basically what their use case could be. Basically, the specific cases would be required and completely, a whole video just on each of these data structures. So after that, we need to focus on the next data structure, which is stacks. So what we need to understand about stacks is they're based on their data structures based on the last in first out principle. So let me just write number 3 and write that on the screen. Stacks. So what is the last in first out principle? Imagine you stack use the word stack as I think you'll understand here how simple it is to understand this. You have a stack of plates, right? So when you need to pick up a plate, We'll probably, let me actually draw that out in so that we can understand that better. So let's presume this is a table, right? This is a table, right? On this table, we have a stack of plates, right? Let's say this is stack of plates. You come in and you wash your plate and put it right at the top. Now, this is good. This what I'm talking about. This is the LIFO principle, last in, first out principle, right? So what do you mean by that? So this is a stack of plates. You wash your plate, and this red plate is the plate that you placed. Another person comes out and he needs to use a plate. Will he go to the bottom and pick this plate out? No, he won't do that. He'll pick the plate right at the top and use that. So that is what the last in first principle is. The item going last in the workflow, or the last function you call, is the first function that's executed. That's the stack principle. Last in, first out. Based on that premise, you need to understand that stacks are very useful for managing tasks or operations that need to be undone, like the undo button in your software that's used commonly. And that basic reason for that is the best implementation for that is using stacks data structure to do that. Given that we're done with stacks, let me move to the related, honestly, data structure that's similar to stacks but in complete opposite, which is queues. Queues are similar to stacks, but the difference is that they're based on first in and first out principle, basically. Unlike stacks, which are based on last in, first out, queues are based on first in, first out principle. Let me write that down. FIFO. That's the principle queues are based on. And how do we explain this particular concept, right? So imagine this is a ticket booth, right? This is a ticket booth. Please don't mind the drawing. So this is a ticket booth, and then we have a screen here. This looks a little messy. Yeah, and this is a guy standing here who's dispersing tickets, right? And in front of this ticket booth, we have a large line of individuals standing there, right? I'm just gonna, yeah, let's just use, imagine just this cyan color is people standing here, right? So we have a lot of different people standing in front of the booth, right? So 3 should be more than enough to at least, get at what I'm trying to say here. So imagine people are sitting here. Imagine if it's the LIFO principle, would someone be able to jump in line, come at the end, who's at the last of the line, and get the tickets first? No. No one would allow that. The people standing in the line would not allow that, let alone the ticket counter guy would not allow that as well. So the FIFO principle basically means that this person came in first, so he's right at the front of the line. So this is the first person who's going to get the ticket and move out, right? So the first person that comes in, the first task that is executed must be completed first before any other task below it would be executed. That's what FIFO is basically. So that is what queues are. When we talk about queues, the perfect case for queues are scheduling tasks in order, like print jobs or customer service requests. So if you want to do something in order, or schedule tasks in order, the best data structure to use for that are queues. With that out of the way, we'll move on to another concept, which are hash tables. Now, hash tables might sound very harsh or very difficult, in the sense that you might hear it like yeah, this is something that would be difficult. No, it isn't. It's a very simple concept as to exactly what hash tables are. And once you understand that, you'll see that this is not difficult at all. What's difficult is having the notion that something is difficult, and then your mind reinforcing that notion until you actually your mind reinforces something easy as difficult, and you know tell yourself, yeah, this is difficult. That's what makes things difficult. So hash tables, simply speaking, if you look at a dictionary, a dictionary has a word and its meaning, right? The word is the key, and the meaning is the value, right? If you want to think in computer science terms. And if you use Python, uh, I think you should already know hash tables are dictionaries in Python. In Python, hash tables are called dictionaries because that's what they are, right? Uh, in Python, hash tables are dictionaries. Let me write this down. So what you need to understand from this is a hash table is basically a dictionary, just like the dictionary you have at your home. It has a word which is the key, and associated with that word is the meaning of that word, which is the value. So hash table basically stores a pair of values, a pair of an item as a pair, which has key value pairs basically. Key would be the words, the key would be the thing that we look up something with, and value would be the value of that key itself basically. So that's what hash tables are in effect. Another aspect to look into understanding hash tables is that if you have a phone book, when you look up someone's name, that is the key. And if you and right next to that person's name is his phone number, which is that key's value. That's what hash tables are. So a potential use case for hash tables is the efficient lookup, quick lookups, and managing associative data like dictionary. That's how the potential use cases for hash tables. Similarly, the next data structure let's move to the next data structure that we need to look into, which are trees, right? So what are trees? Trees are basically representations of hierarchical data structure made of nodes, with a single root node and subnodes branching out, right? So that's what trees are. And it's basically representing hierarchical relationship between data types. At this time, I think I don't want to get into too much detail about nodes, but I think it's correct for you to presume that nodes are spaces or data points where data is stored. Let me use a different color here. Let's use the same blue. So we have different nodes here, basically, and they have values 1, 2, 3, and they're connected, basically. So this is basically what a tree is. Basically, it sets out relationship between a root node, which is the first node with the highest on the hierarchical level, and the branching nodes, each under and each having a relationship with those above it and those below it, basically, right? So it's just like family trees that people draw, with each node having children nodes, right? So nodes below a node are children nodes. And generally speaking, uh, they're used in scenarios. For example, there's Dijkstra's algorithm to find the shortest path route. That's usually used on trees. Basically, you set up nodes of different length, and then we find distances between those nodes using Dijkstra's algorithm. So what you need to understand mainly is in 3D spatial based software, nodes are and trees are used a lot in that capacity as well, and especially it's used in cases scenarios where data needs to be structured like hierarchy, like databases and file systems, basically. On that note, right, so if you've used Windows 10 or something, you'll notice that you have on the file explorer, you might have a folder here, right? And there might be an arrow here which is something like this, but when you click it, it becomes something like this, right? And under this you'll find uh, uh, items within that folder that weren't accessible until you expanded that folder on the side panel, right? That is what basically trees code. This is how the way we are doing this is using a tree data structure to set that up, basically. So that is how this is done. So based on that understanding, I think you have a general idea of why trees are important. Similarly, let's move on to the last particular concept that we need to discuss. And again, like I might want to add here, the Dijkstra's algorithm I've given example is just a way to explain what's happening with trees and nodes. Mainly, Dijkstra's algorithm is focused towards the last data structure that I think I messed up. So 5 This was trees was 6, not 4, and this is 7, not 5, right? So graphs is where Dijkstra's algorithm is related to main. So when we talk about graphs, what do we need to understand with that? So they're a collection of nodes or vertices connected by edges, basically, right? It basically means that you have nodes just like I talked about before, and each of this node, the surface is known as vertices, and these vertices are connected to each other. That's what we mean by graph. And Dijkstra's algorithm basically finds the shortest path through these vertices. Like that's what Dijkstra's algorithm was. It basically develops a network-like relationships between different nodes within data, which are data, right? So a test case could be like if you in social media platform you have an account, you're a node, right? And you're connected to the edges of other nodes, which might be your friends on that social media account, basically. So the ideal use case for such a data structure is usually representing relationships like maps or social networks. What we need to understand at the end of this video is that choosing the right data structure depends on the problem you're trying to solve. Arrays are simple but limited. Linked lists are flexible. Stacks and queues manage order. Hash tables offer quick access, and trees and graphs handle complex relationships. Understanding these data structures helps in writing efficient, scalable code that helps you move forward, and it also prepares you for potential coding interviews ahead. So with that, we're going to wrap this video up. If you got any value from this video, please like and subscribe, and let us know in the comments below if there's any topic, any concern, anything you want to tell us. Let us know in the comments below. We're going to wrap this video up. We'll see you in our next video. Thank you.